the usual application of the formula for variance applied to the sample data, and the other with a modification that the division of the square of the sum of squares of the deviation from sample mean was divided by 1 less than the sample size. Okay, and then we saw that this was a biased estimator and this was unbiased estimator. So, okay, if we're into statistical analysis and we're trying to estimate, trying to get some idea about population parameters, and we have sample data, we would be looking for estimators, and the first task should be to look for unbiased estimators. Now, the bias estimator that I have listed, uh, just tell me which way the bias is going to be. Is it going to, on average, underestimate the parameter or overestimate the parameter?
So underestimate.
Exactly, because the denominator is larger. So, if this is theta or n square, the distribution look like this. The distribution should look like this, and I've approximated this with normal distribution, which would be when we can take a very large number of samples. Okay, so although for any particular sample, we can't expect the estimate to be exactly the same as the value of the parameter, but if we have an unbiased estimator, then we're going to have many more samples with values much closer to the true population parameter. Okay, that's the first task. Which was it? I suppose it was example 6.1 or 6.2, where there were multiple estimators in example 6.1 or 6.2. Okay, before sending it to you, I'll check which example it was and I'll correct it. There were multiple estimators of the population mean. Okay, I'm taking these two here, although we had 4 listed there. So X bar is population mean, X tilde is population median. Both are unbiased.
So, sir, like to estimate the population mean, how can we use the median as an estimator?
Okay, now this is specifically referring to the example, okay, where we were given that the population is approximately normally distributed. If you have population approximately normally distributed, then mean and median are same. Okay, so if we use sample median to estimate population mean, even that is going to be an unbiased estimator. On average, if we take many samples and average of median of those many samples, we're going to be pretty close to the population mean. Okay, but still there's a problem with the sample median being used as an estimator of population mean. I'm going to list it. It's not perfect, I would say. I would make the statistical claim that sample mean is still a better estimate of population mean. Both are unbiased. That is true. Okay. Now, if we have more than one and there's a particular quality that we want, which is present in both, how do we select which is the better of the two? Then we put another restriction. You should next be looking for an estimator which is efficient. Efficiency here is defined in terms of variance. Let me just use the word variance here. Variance of sampling distribution of the estimator. Which brings us to the next subsection, which is the minimum variance unbiased estimator. Suppose theta 1 hat and theta 2 hat are two estimators of some population parameter theta, and they're both unbiased. Okay, so we can compare this with the example that I just gave. Let's say this theta is the population mean, theta 1 tilde is sample mean, and theta 2 tilde, not tilde, theta 2 hat is the sample median. Okay, so we can have the sampling distribution of one estimator like this, sampling distribution of another estimator like this. Obviously, the one which has the lowest sampling variance as the best estimator that we should be looking at. If you say that this is the distribution of theta 1 hat, this is the distribution of theta 2 hat, then theta 1 hat is the efficient estimator. It's the minimum variance unbiased estimator. Okay, now I'm going to reproduce one sentence exactly as it is in the text. Okay, so now we have a lot of ways theoretically to find the minimum variance unbiased estimator. Now let me again make this claim for a sample. I should not for sample denoted by x1 to xn from a population with mean mu and standard variance sigma square estimator of population mean denoted by mu hat, and if we use the sample mean, then this is the minimum variance unbiased estimator of the population mean. I'm not going to prove it here. And the last thing, even if we can figure out which is the estimator which has the minimum variance, we still need to know, okay, or the readers of analysis would still like to know how good is the best. For that, we should report along with the value of the point estimate the standard error. Okay. I could have written the sampling variance as well, but standard error is much more common. This is just the square root of the sampling distribution of a parameter. Okay, to be very specific, let me write it in this notation. Suppose we have a population. Okay, so the subscript here is uppercase N for the last. N uppercase N is the population size. And sample denoted by x1, x2, all the way to x sub n. Okay, so this is a smaller case n, the last subscript of sample. You can have realizations sample 1, sample 2, all the way down to sample m. Just to differentiate, let me put superscripts here to denote which realization this is. Okay. If we have a sample, we can have sample mean as well. And we would have realized values of sample mean. The superscripts are for the samples. We can also have sample variance, where S square means that we're dividing the sum of squares of deviation from sample mean by n minus 1 not n. So we're going to have smaller case. So I'm putting comma 1, comma 2, comma m to denote that these are particular values obtained from the samples. So the distribution, this distribution is the sampling distribution of sample mean. Okay, this would have some variance as well if there's a distribution. So let me write this as variance of x bar. And the square root of variance of x bar, we will call it standard error of x bar. Similarly, this is the sampling distribution of sample variance. This is where it gets confusing. You already have an estimator which itself is variance, and you have a distribution. This distribution of sampling variance would have some variance as well. Okay. Let's denote this by variance of x square, and standard error of this, uh, the square root of variance of s square would be called the standard error of s square, which would measure how reliable s square is as a estimator of the population variance. Okay, so it's a good practice to just write down the standard errors of the estimator alongside the reported value of estimate. This, which color should I? will be used a lot in econometrics. So we'll see that we will have samples, we will run our regression, get values, particular estimates, and we would report the standard errors alongside. Yeah, there's one further complication. I should write expression might include parameters value. Just a moment. Shh. पंचायत लग रही है मेड्स की. Okay, expression for standard errors might include parameter value themselves. Obviously, we won't have true parameter values. We'll have to substitute estimated values of parameters in expression for standard errors. Then we'll call those expressions the estimated standard errors. Again, this would happen a lot in econometrics. Okay, let's see how this will be. So this is example 6.10. We have the estimator for population proportion as the random variable divided by the sample size. Okay. Now this is the standard error of the estimator denoted by this. This is the square root of variance of the estimator. You've seen the estimator itself takes this value. Okay. Now n would come out n square variance of x, and we're speaking here of a binomial random variable x. Okay. The variance of the binomial random variable is n into p into 1 minus p. We have n square, so this becomes p into 1 minus p divided by n. Okay, so we have this situation. The expression for the standard error of this estimator includes the true population values p and 1 minus p. Obviously we don't have them, otherwise why would we bother? Standard error of P bar. We would have estimated standard error of P bar if we replace P with its estimator. Okay, that's all I have for you today with